I hope everyone had a good lunch, and thank you for coming. Who has been listening to the background music? Can I get a show of hands? And for those who are on the webcast, if you have not heard the background music, it sounds something like this. Baroque, classical, a chorale, actually. It almost sounds like it was written by Bach, except it was written completely by an AI. And so was the background music that we've been hearing this morning. Now, if you were confused, I don't blame you. And if you notice something weird, then I actually commend you. I challenge you to go to BachBot.com and take the online musical Turing test. So far, out of the 1,800 participants we've had, only about 5%. They do only about 5% better than just randomly guessing which one was Bach and which one was not. And today, we'll be going over exactly how BachBot works, and we'll take a look at some of the amazing discoveries that we found while producing it. My name is Feynman, and today I'll be talking to you about composing Bach chorales using deep learning. So the big questions that we're going to touch upon today are the following. Where is the frontier of computational creativity? At what point does a machine stop copying and start innovating, creating new forms of art? How much has modern machine learning techniques, such as deep learning, advanced the field of automatic composition? You know, before deep learning, most of automatic composition used symbolic methods, such as this in text, where you build trees and you build symbolic structures, and you try to use that and use rules to generate new music. However, in the era of deep learning, we use these more sophisticated models, and we're able to produce some pretty surprising results, as you'll see. And finally, how do we evaluate these kinds of models that generate new data, that generate new forms of work? Is it just copying? Is it actually producing something new? What's a good way to judge how well this machine learning algorithm is performing? For those who are impatient, here is the quick summary about what we'll go over. If you are in a rush, take down these 3 notes and you're welcome to leave. BachBot is a deep recurrent neural network model that is capable of polyphonic, meaning multiple voices, automatic stylistic composition, and harmonization. And I'll go over exactly what that means in more detail later for non-experts. We also find that it learns music theory, such as cadences, tonics, scales, without any prior knowledge. And this is really good, because this kind of validates what we're teaching in music theory classes. The kinds of theories and techniques that we teach there are especially helpful and automatically discovered by machine learning to help create new music. And finally, in a musical Turing test that we conducted with over 1,800 participants now, their performance is only 5% better than just randomly guessing which is Bach and which is not. And by the way, for the engineers and hackers in the room, everything I'm going to talk about today is open source. If you would like to run the original code, I've put it in a Docker container, and I have instructions on this URL on how to download and run it. If you do not like messy research code, then I recommend the TensorFlow implementation that the Google Magenta team has so kindly provided for us. So this is the high-level overview of the talk. We'll start by introducing sequence modeling, and then we'll specialize it into the domain of music. We'll then see how deep recurrent neural networks, a model from modern machine learning, can be used to build models over these sequences and then sampled to generate new music. And finally, we'll unpack the black box of this recurrent neural network. We'll take a look inside, and we'll find some interesting discoveries related to music theory and art. Let's get started. I want to start off by talking about sequence modeling, and we'll do it in a familiar domain, which is text. So suppose I gave you this sequence of text. The quick brown fox jumps, and I ask you, what word comes next? Over. Oh, someone seems to be a programmer. Higher. Another one, also valid, yes. These are the ones I came up with. over, because lazy dog obviously comes after. But other words that could have worked here, around and lackadaisically. Now, over seems to be the more dominant answer. Most of us would believe that jumps over seems to occur much more commonly than jumps lackadaisically. How can we encode this kind of intuition mathematically? Well, one way is using probability theory and something called a conditional probability distribution. And what this means is really, if I see the quick brown fox jumps, then the probability of the next word being over is 75%, which is higher than around, and both of those are much, much higher than lackadaisically. And this kind of captures our intuition. Over is probably the most likely word that we're going to see after this string of text. Now, a problem with the way I wrote this representation up here is that it doesn't generalize very well. You probably don't see the sentence, "the quick brown fox jumps," very often when you look through a string of text. But when you see the word jumps, you know that the word after jumps is likely to be over, around, or lackadaisically. You didn't really need all of that context at the beginning. And so one way to kind of get around this potential problem of not seeing every possible sequence of text, but still to be able to generalize, is to just truncate. And so I did exactly what I said in the previous slide, which is, well, after the word jumps, over, around, and behind are all pretty likely. And we'll just model it like this. We'll forget everything before that and just start at jumps and say the probability of the next word is this. This is actually called the 2-gram model in language modeling. And with just this model, we're able to generate new strings of text. For example, we can start with the word I, and then given that I saw I, what's the probability of the next word? Am is fairly likely, so let's say we picked that. And then we iterate and repeat, and we can end up with a string such as I am enjoying GOTO Copenhagen. Now, we didn't need to just stop at 1. In fact, we could have had longer and longer contexts. Rather than just looking at the 1 previous word, we could have looked at 2 words back, or the last 3 words. And unsurprisingly, as you take larger and larger contexts, you generate more and more convincing texts. Over here I have, for example, we've trained a n-gram model, 1 grams, 2 grams, and 4 grams on Hamlet, and we try to generate some random Shakespeare. The 1 gram doesn't do too great. To him swallowed confess here both, which of save on trail for R.A. device androt life have. I don't even know if that's grammatically correct. Sounds like Shakespeare? Well, how about this one? King Henry, what? I will go see the traitor Gloucester, exeunt some of the watch, a great banquet served in. I almost believe that that came from Hamlet. That's all I want to talk about at sequence modeling. We saw how we can model sequences using probabilities, and we saw how we can generate new sequences by sampling given the previous words that have occurred. Now let's do a little bit about music so that we can do sequence modeling on music. Modern music notation looks something like this, where we have these notes, and depending on where they occur, that's kind of how high or how low the pitch, and depending on how the note looks like. So this note versus how this note versus this one right here, those denote the note's duration, which we'll also look at. There's also this funny symbol up here, which turns out to be super important, and some symbols over here which are less important, and we'll cover all of those in the following slides. The first thing I want to talk about is pitch, or how high or how low a note is. And in music notation, it's denoted by. So what you just heard there was this sequence. And as you saw, as these notes got higher and higher on these bars, the kind of pitch sounded higher and higher and higher. It was increasing. With pitch out of the way, the second attribute of a note that is important for us to model is the duration, how long that note is. So in this example, we're seeing notes that increase in their or decrease in their duration. They're occurring faster and faster, and they're denoted by kind of this circle versus this filled-in circle versus these circles with bars on top of them. Polyphony. This is one of the words that I used when I was giving the TLDR, and it refers to the presence of multiple voices. So in particular, in Bach Chorales, there are 4 voices: the soprano, the highest note, the alto, the tenor, and the bass. And we need to model all 4 of these voices in order to produce interesting chorales. One way to take the pitch and the duration and the multiple voices and to represent them in a very convenient format for computers is in this format called the piano roll. So when I think of music on the computer, I think of it like this. The pitch here is on the y-axis, where the higher it is, the higher the pitch, and time is on the x-axis. Each of these bars denotes a note, and depending on how long that bar is, that's the duration of the note, and depending on its position here, that's the pitch of the note. The color is to help visualize. OK, the last structure, and this turns out to be a very idiosyncrasy of chorale modeling. It's actually surprising how much performance deteriorates when we don't include this feature. It's the fermatas, this funky little hat thing. You'll see that in our encodings, we explicitly represent these fermatas, whereas we neglect things like the key. And the reason for this is as follows. In Bach's music, the fermatas are often used to help denote the phrasing structure, this idea of this segment of music is coming to a close. We're about to enter another segment of music, or this entire chorale is ending now. It's used for emphasis and used to delineate separate motifs within a piece. Great. We are now armed with all the tools from sequence modeling and music theory that we will need to generate Bach chorales. But how do we turn Bach chorales into sequences? Well, the first thing to do is to grab the Bach chorales from some data source. In my case, Music 21 has conveniently transcribed most of Bach's chorales from the BWV collection into a format called music XML. So this is structured markup that we can use on a computer to build the piano roll and to build our sequences from. The first thing that we do is we remove these funky symbols over here. It's called the key signature. So notice over here we have these two little kind of B symbols, and they're absent over here. But the notes have also been kind of shifted. This one got shifted up. You know, it was on the line. Now it's in between the two lines. And same with everything else. Another pre-processing step that we do is we quantize to 16th notes. And so what I mean by that is take a look at this funky 30-second note right here with 3 bars underneath it. In our pre-processing, we quantize that to just 16th notes. So over here, they only have 2 bars now. And we'll justify both of these transformations in the next 2 slides. Transposition is justified because it preserves relative pitches. You can tell whether a piece is shifted a little bit lower, a little bit higher, but it's still the same piece, more or less. And I'll demonstrate this with an example. Right? Same ascending 5-note sequence, just the first time in C major, and the second time up to G major. Quantization. This one's a little bit ugly. What we basically do is we take 16th or 30-second notes or anything faster than that, and we just squish them together so they're 16th notes. And it only affects 0.2% of the data set. As you can see, these 30-second notes here are gone. But it's not completely justified. It's a little dirty trick that we have to do in order to make the problem tractable. Polyphony is the interesting problem, the presence of multiple voices at the same time. So I have a question for the audience. Suppose we're working with modern music, so 128 pitches in MIDI. How many chords can we construct with 4 voices? Way too many. That is a very good answer. It's exponential in the number of voices. So you can imagine on a piano, this is 128 to the 10. And you clearly don't actually see all of these chords in Bach's music. In fact, I would argue you see very few. As this plot shows, the most common chord occurs 7.5K times inside of our data set, and the 40th most common occurs less than 200 times. So representing it as all possible 4 sequences for chords isn't going to work for us. And this is kind of the key novelty of BachBot here, is how do we work around polyphony? And this is our answer. We serialize things in soprano, alto, tenor, bass order. And so what I mean by that is even though this chord right here could be interpreted as a distinct symbol or word in our sequence, instead what we're going to do is we're going to encode it as 4 different words. The soprano note, the alto note, the tenor note, followed by the bass note. And then we advance time to go from this chord right here into this chord right here, which we denote using a frame delimiter like that. And we repeat the process. Soprano, alto, tenor, bass becomes these 4 notes. The Boolean value here indicates whether a note is articulated or whether it is connected from the previous note. And this allows us to handle duration. So in the first case, since these 4 notes were all played at this instant, they were all articulated. But in the second case, these 3 were connected, so it's true. And finally, the pesky little fermatas, which I've used this clever little symbol to denote. Since there's a fermata here, we have these little symbols inside of these frames. And over here, this is your sequence. This is the musical sequence that we're using to represent this piece of music over there. Great. So we're all set about what this data looks like, what we're trying to model. Now we got to figure out how do we define a conditional probability distribution over these. And the way we're going to do that is using something called recurrent neural networks. So recurrent neural networks are built from basic building blocks called neurons, and they look something like this. I have some input. In this case, these could be words. And these words have to be embedded into as numbers somehow. So you could use, for example, a vector where you have a 1 representing where that word is, whether the first word or the second word or the third word. Or you can do more fancy things. But the inputs are then weighted using some weights and added together, and then passed through an S-shaped function, which I'm just going to denote as sigma in order to give an output. And so this is called an artificial neuron. It doesn't really represent how human neurons work, but it's a very convenient computational abstraction. When you take them and you slap them side by side, you get something called a layer. And when you take the layers and you stack it like this, you get something called a feed-forward neural network. And so in math, you write it like this. The inputs here, x, are weighted using this weight matrix W, representing this first layer, and then pass through this S-shaped thing to get the outputs here. And then these outputs are treated as inputs to the second layer, weighted again, and then pass through an S-shaped thing, and it's repeated over and over and over until we get to the top. Now, of course, with music, we have to pass context over time. For example, we need to know what notes had came long time before so that we can have a musically consistent or coherent and consistent piece. And the way that we get around that is we have to introduce this notion of memory into our sequence model. And so the way we do that is we add this recurrent correction, giving the name recurrent neural network. So this right here, or sorry, this input followed by this hidden state and this output, that is that network you saw in the previous layer. The new part is this connection here, where we take the hidden state, delay it by 1 time step, and then pass it back in. And the reason why we do this is we think of this part as kind of keeping track of all the stuff that's already happened, the musical context, and this as the current input, the last note I just saw. And so you combine what note did I just see with what is the current musical context that I'm in order to help predict what is the next note I should output. So I drew the memory cell as kind of this kind of black box in the last slide. It's not too important to understand this, but the specific memory cell that turned out to work very well for us is something called a long short-term memory cell. So this memory cell here really looks like this inside of our model, but it's not too important. In fact, I'm actually going to draw it like this. So this little kind of gray box here is the memory cell. And this here is your neural network. Music is a sequence over time, so you view this sequence down here as the start symbol, 49 true, 50 false, frame delimiter, fermatas, as these symbols down here. And you can kind of just unroll this delay into these different units, and you form this unrolled network over here. And this is what you need to do in order to train, as we'll see in the following slide. But here I kind of want to show that this is what I'm going to call stacking. We're making the network deeper and deeper by adding more and more hidden layers. With the network now unrolled, we're now faced with the question, how do we make sure that the network is good at predicting what Bach would have written for the next note? And the way we do that is using something called the sequential prediction training criteria. And here I've shown it again for text. In this case, what is the next character given the previous character? So you can see here, given that I've seen the character H, I need to predict the character E. And given that I saw the character E, I need to predict the character L. I'm trying to predict the string hello, by the way. And the question now becomes an optimization problem. How do I jiggle these weights around so that when I see H, I assign high probability to E? And so if you do the training, what we've done previously is specify the RNN dynamics, so the recurrent neural network, and how to stack it, and how to pass it forwards through time. You can kick it off by setting the hidden state, this H0, to be all zeros. And the goal now is to jiggle around the parameters so that the probability distribution over sequences is very, very high for what Bach actually wrote. At least we want our model to predict what Bach actually wrote is correct and with high probability. And this is kind of what it looks like if we use that probability of Bach chorales as our training criteria. You see that as you train more and more and more, the kind of error goes down over time. However, a different story emerges over here on the test set. So now, on the test set, what I mean is we hold out some Bach chorales so that the model doesn't just memorize everything. Rather, it has to be able to generalize. And we see that, OK, again, the error is decreasing as we train more. But as we add layers, more and more layers, in the training side, adding 4 layers seems to give us the lowest error. But in validation, adding 3 layers the red line here seems to give us the lowest error. And so this is actually how we chose our design. By looking at the cross-validation loss, we're able to see that the 4-layer network was memorizing too much, and that the 3-layer network was better to generalize. And so we use this technique here to help choose the architecture for what is the optimal model hyperparameters to use. So are you ready for some music? It's not going to start out very great. So if we just train for 100 mini batches, BachBot sounds something like this. OK, I'll spare you. We can train for 5 times longer, and we'll get something a little bit more coherent. It's all right. We definitely noticed some mistakes there. Couldn't pass as human quite yet. What if we quadruple the amount of training time? A little bit better. We're starting to see longer-term phrasing structure, but also some very obvious errors that kind of give away it's generated by AI. What if we increase the training even more? At 5,000 mini batches, this is the music that you're hearing for the background music. Not bad. Passable as conference background music. Thank you. Now we move on to the demo side and the discoveries. So after building this model, training it, what can we learn? What can we conclude? What are the research findings of doing all this work? The first thing that we're going to look at is the hidden states. So remember those little gray boxes? Well, what happens if we look inside of them? It turns out if you just look at it naively like this, you reach the common conclusion that a lot of deep learning critics have, which is deep learning is very hard to interpret. I'm plotting the hidden state here. So basically, you can think of each of these as a cell in the hidden state. And on here, I have the time axis. And to me, honestly, there's some patterns, right? This clearly looks like a note that was held for a period of time. And it's like this band that goes down through all of them. But I can't say anything too insightful here. However, when we zoom into the later layers, so the layers closer to the output, or like the top layers of our network, things look a little bit more structured. In fact, this here kind of almost reminds us of the piano roll. And if you think about it, it should, right? Recall that the model is supposed to try to predict the next note. And so if the model is doing a perfect job, then this last next note prediction should be nothing more than the original piece shifted one note forwards. Here's the connection to music theory. If instead of looking at the neurons over time, you look at a specific neuron and you look at when is it firing, when is its output really high, and when is its output not high, you arrive at a plot like this. And you see there are peaks where certain neurons exhibit really high activity. And I'm not a music theorist, but one of my collaborators is, and he was able to discover that these neurons, for example, layer 1 neuron 64 and layer 1 neuron 138, they're in perfect alignment with perfect cadences with root position chords in the tonic key. And similarly, he was able to give interpretations for all of the other neurons. The details are in the paper, so feel free to take a look at it if you're curious about this. This is the part that I find the most exciting. In addition to harmonizing, or in addition to automatic composition, where we generate music that sounds like a Bach chorale, we can also ask the question, what if I force the soprano line to sound like this? And I was to ask Bach, or BachBot rather, harmonize this. Make it sound like a Bach chorale. Make it sound like it was written during the Baroque era of music. Not bad. Thank you, thank you. But this got me thinking. This got me really thinking. Well, hey, I can harmonize a C major scale. You know, what else can I do? You know, can I bring Bach back to life? You know, Twinkle, Twinkle, Little Star was a piece that was written well after Bach's death. But what if Bach was alive for it? What would a Bach remix of Twinkle, Twinkle, Little Star sound like? Thank you. And I'm kind of betting on this one. Since there's 1,600 people, I'm hoping it's someone's birthday today. Please stand up if it's your birthday. Thank you. So for you, I want to tell you that BachBot wishes you a happy birthday. Thank you, everyone, for your attention. That's all I have for this talk. And I'll open it up to questions now.